You have seen this diagram here. What is the overall components you have for a solar charge maximizing controller system? But this lecture we stay focused on those components used in that system. First, you start from a solar array. Normally, you have MPPT system. You have all the arrays connected in series. That will be connected to the input side of the solar array. Say this side here is a series connected solar array, and then you can wire that to the MPPT solar charge controller. You still have that here. You can have a second array is also like a series connected. But the unique in our system is we have another array. So it's the down bottom here. It's called parallelly connected solar array. It connects to the solar charge maximizing controller through the split bolt wire. We call them a split bolt wire because the MC connectors is not enough to handle the current we have. MC can go up to 24 amps, but we would have to handle 120 amps here for the split bolt this wire. We call them PVS, so it's very unique, this terminal here. We call them a split wire, PVS, get connected to the solar charge maximizing controller to be controlled by the mechanical switch. And another important component in our system is the LFP. This lithium iron phosphide battery must have a battery management system built inside because we want to make sure the lithium iron phosphide, this cells, as you know, 24-volt system, you got an 8-cell built inside, connect in series. The battery management system has to charge them equally and to protect the battery in high voltage situation or low voltage situation. So this is very important here. We must have this battery bank, lithium iron phosphide battery bank built inside. So this whole system, we call them solar charge maximizing controller system. And we say that parallelly connect this power still available for MPPT solar charge controller, even when the solar charge maximizing controller and the mechanical switch is open, is off. And normally our system would also include the DC load. Remember that we have a lot of DC current coming during the day, and then if you don't need to build this battery with a huge capacity, and then you would expect the system to spend some load during the daytime. But you don't have a lot of like a load run during the day. Household load may be not that much during the day. So what we'll suggest, normally this solar charge maximizing controller system would include the DC load during the day, like can be used, can be spent, the power. And that would be EV chargers. For 5 kilowatt system, 10 kilowatt system, we very easily can build class 1 and class 2 EV chargers. That is like a class 2 would be about 6 kilowatts, so 30 amps, like a 240 system. So that can charge EV in a few hours. Because the system will power the DC load directly without even charging the battery, without even sacrificing the battery charging cycle. So the best power source is here to be used for green hydrogen production. We know that we have proton exchange membranes cells, PEM, and then anion exchange membrane cells. They all can produce the green hydrogen on site. And we're going to give a little bit touch how the system would have to be built to be able to store like about 30 psi this green hydrogen in a cylinder on site to be used as fuel or as a fuel cell. So if you would ask what is a solar charge maximizing controller system, so you could define that the solar charge maximizing controller system would include a PV array with a solar charge maximizing controller connecting all the panels in parallel, and also include the MPPT solar charge controller connecting the arrays that have been connected in series, and also has a solar energy storage battery. We use that battery to maintain, main function is to maintain the operating voltage of the system. So you can maximize the energy harvest because you maintain the optimal this voltage. And that system will normally include a solar inverter as well to span the DC node during the day, because you have that DC node powered from the solar array directly. That solar array is another unique point is they can be connected in both combination series and parallel, and those number of the panels not necessary to match. It's very flexible. You can arrange the series connected, parallel connected according to the capacity of the MPPT solar charge controller based on the voltage of the MPPT solar charge controller and the currents that maximum can handle by the MPPT solar charge controller, and the maximum current can be handled by the solar charge maximizing controller. In terms of the load in the system, it can include off-grid PV system or grid-tie system, and it's hybrid, or this grid-tie with this net meter, or off-grid hybrid system without grid-tie this net meter. So it's very flexible, the system. We would like to show you this diagram again to explain what's the principle of this solar charge maximizing controller system. Because you can see clearly you have this solar array that being connected in series, that get connected to the MPPT solar charge controller, and then you also have the array in parallel to be connected to the solar charge maximizing controller. And this terminal here we call the PVS, because the split both wire we are talking about, to expect that wire to handle high capacity of the current, high current capacity. And you have the battery here to maintain the voltage. And here we say you got a common negative here. We are going to get into the very detail that what is called a common negative MPPT solar charge controller, and then what is called common negative solar charge maximizing controller, because they share the common terminal negative here, the same this potential point that can be connected together. In common negative MPPT solar charge controller, the PV negative and battery negative can be physically connected, or lots of time they just actually connect inside the MPPT solar charge controller, and that has to match the common negative the solar charge maximizing controller. We say you cannot mix them up to charge the same battery bank. And that system also include a solar inverter or some kind of DC load. So it's clearly, it's better explain what is a solar charge maximizing controller system. Because we talk about solar charge maximizing controller is only one component, but if you talk about the system, it's actually include the whole system, what we have here. Most of the time, you would have definitely include an inverter as well, but necessary component would be solar array, and solar charge maximizing controller and also the battery bank. And here is very unique, our system. It always has a split bolt wire. So that split bolt wire being there to be connected to the solar charge maximizing controller to handle the high current we have for the system. So you know that the solar charge maximizing controller system include a very important component that is called LFP battery with the battery management system, BMS. Any of the LFP, this battery, if you open it up, you always see this battery management system control board inside, with lots of wires going out connected to the cells. Like you have a set of the wires goes to each cells for this 24-volt system. They actually control boards here would be able to sense the voltage of each cells, and when they charge, they try to balance the voltage, make sure not one cell to be overcharged and the other cells don't get enough charge, because in that case, that cells can be damaged, or overcharged or not enough. To discharge too much below like 20 volts, the cells can get damaged for 24 system. For 24 systems, the battery, we want the battery operating voltage to be 25.6 and 26.5. That is between 20% and 80% state of the charge of the range. That's most appropriate range for the solar charge maximizing controller to work at that range. So this is very typical, unique 100 amp hour, this LFP battery. It has a 50 amps charging discharge current. So here you can see very clearly why the charging discharging current has to be limited by certain C rating, 0.5 C or 1 C. Here's the reason why. You see the wire here they use inside? It has a certain gauge numbers. If they use a heavier gauge inside, they allow you to draw more currents at once. So the current's charging discharging capacity is all limited by the wire size they use inside. So it's very important to read manufacturer's specification. What is the C rating? You can have a 500 amp hours this battery, but you may only need have like a 50 amps charging discharge capacity if you use the same wire gauge here, right? But if you use heavier gauge inside, then can 500 amp hours battery can go up to 250. But that's how they normally make to make it 0.5 C. So it's always checked that it's not necessary. They could make a huge capacity of the LFP battery, but to give you only small amount of this charging discharging capacity, which is C rating. So it's very important when you specify the system, you check into the specification and make sure you specify that what the C rating must be. So you know that how much current it will take. So this is very important to make sure the system will function properly. So this is kind of summarize what we would expect the LFP battery with a battery management system to do. Here's the battery with the BMS. We normally would want to have the system maintain at the 20% to 80% charge, maximum go up to 90% charge. Try not to run them 100% charge, and then the battery management system will shut it down and then causing troubles, because you no longer be able to take the current from the system, and then eventually it will cause the solar charge maximizing controller to shut down as well, because that controller is also set by the voltage. If the system voltage is too high, they will shut it down, so you'll not be able to charge anything, not be able to power the DC node, because high current would have to go through the solar charge maximizer controller. When they sense the high voltage, both will protect, and then you have no power for the load. That's why we have the narrow working the voltage range. That range will match the PVS, the panelly connected, or the panel's nominal voltage. Remember that? 24 VDC nominal voltage. What's the range? That PVS, PV split both wire voltage, has to match the nominal voltage of those panels. Of course, the panels are going to be a little bit high, and then you size the cable to have enough preserved for their voltage drop. We found that the lithium iron phosphate battery has a higher C rating. Normally they make it 0.5 C, but you still, like what I mentioned, you want to confirm that with the manufacturer's specification paper. Some you say other batteries, even you build a battery management system for them, deep cycle battery, normally they only get the 0.1 C rating. So if you have 100 amp hours, you only get 10 amps to be charged, to be charged for that battery. So even you try to build this AGM, this battery sealed and looks good, but it's not appropriate to be used in the solar charge maximizing controller system because of the C rating is lower. And then you still have to build your own battery management system for that. It's not going to be easy. Also, this battery, lithium iron phosphate battery, has longer this lifespan. Many manufacturers, they kind of give you minimum of 5 years warranty, and then you can expect them to work like for 10 years with no problem. And they say nowadays they make it even up to 5,000 charging cycles. Remember we mentioned that the lithium iron phosphate battery, even 3,000, 5,000 charging cycles, you still get the 90% of the capacity left. You can still expect to have a 90% after so many thousands of the charging cycle. Even some other lithium, magnesium, this cobalt battery, after 3,000 charging cycle, they got 80% capacity left. So LFP is actually quite appropriate, lasted a lot longer. But most important is that lithium iron phosphate battery has to work in the temperature range, which is 5 to 45 Celsius degree. That's very important because lower temperature below freezing point, that battery cannot be charged. And it's also protected by the battery management system inside. That's why we're going to get into the detail down there, how to use the system. We have to make sure that battery be located in somewhere with a controlled environment, not necessarily to be comfortable like indoor of the house, but it has to, you have to make sure the cells not to be temperature not to drop below the 5 Celsius degree during charging or during discharge, and not to be too high temperature. You got to do through the ventilation control or some kind of temperature control to make sure the battery has to work in this temperature range, and also humidity, like a non-condensing situation. You do need environment control. It's same as inverters, the charge controllers. So we want to house them in the same location and they give them the proper temperature control, because all the components here will ask for certain temperature range and certain relative humidity range to work, to function smoothly.